Any intuitive guesses? You don't have to justify, just intuitively. I hear one no. So I'll give you the intuition before we come to the answer, and this is strictly intuition only, okay, which is, I mean, it's not rigorously correct, but just to drive intuition. Look at the definition of Lipschitz continuity. I have mod fx minus fy. If I take the mod x minus, the norm x minus y on the other side, what does that expression kind of remind you of? Derivative, right? Now, that means that, i.e., the definition is saying the derivative somehow should be bounded, it should not explode. That's the intuitive feel for Lipschitz continuity, okay. Now, when you look at this function over here, root of 1 minus x squared, is it differentiable, or is there places where the derivative can blow up? At the endpoints, it can blow up, because when I take this derivative, I'm going to get a root of 1 minus x squared in the denominator. So, that's going to be my hint to try to prove this, right. So, for this, what do I need? I need f mod of fx minus fy less than equal to L times x minus y, okay, for all x and y belonging to minus 1. This is what I need to do, okay. Now, as we have already got the hint, endpoints is where some mischief is going to happen, right. So, if I prove that this is not true even at one point, it's over. So, let us choose one of the endpoints. Let us choose y equal to 1, okay. So, what happens over here? So, this becomes mod fx. What is fy? 0. So, that becomes 0, and okay. So, this becomes mod of 1 minus x squared, right, right. And this will have to be what? Less than or equal to, I am going to put a question mark over here, less than or equal to what? L times mod x minus 1, okay. So, now let's take the limit as x tends to, let us say x tends to 1 from the, just from the left hand side of 1, because the other side is not in the domain, right. And what expression I want to take? Basically this 1 minus x squared by x minus 1. What is this limit? I have just taken this guy onto the other side, and I am asking you what is the limit over here. So, root, can I open up the denominator somehow? What's going to happen? We can split 1 minus x squared. I can split it as okay, and I can also write this as root of 1 minus x squared, square root and then square it. It's the same thing. What do I get? Is it clear? It's mod x minus 1, which is the same as mod 1 minus x, and 1 minus x is square of square root. So, can I cancel something? I can cancel 1 square root. I can cancel this guy. I can cancel this guy with this guy. So, what am I left with? Numerator root of 1 plus x, denominator root of 1 minus x. And when I take this limit in mind, if x is tending to 1, does this limit exist? No, limit doesn't exist, right? It blows up. Implies what? I cannot find a positive number L such that this expression is always true. The closer I take x to 1, the more this expression blows up. Therefore, I cannot find a L. So, our our greed was not rewarded, this function is not Lipschitz continuous, right? So these are very subtle points for every function to evaluate whether it's what type of continuity it is, right? So this is a little bit of a generalization from what you saw in high school. Any doubts on this? I mean, this algebra is very simple, right? It is dealing with what are the expressions we use? A minus b into a plus b is a square minus b square. I mean, this is the level of stuff that we did. There's nothing very complicated. It's just applying it intelligently to finding out these constants. Do they exist? Do they not exist? Okay, that's the idea. So with that, I think we have run out of time also. So we can end over here. Yes, question. Okay. Right. Correct. Yeah, but you cannot stay at that constant because the moment I take it closer, that constant gets exceeded. So for the Lipschitz continuity, I need to find an L, and that L has to be fixed for all x and y in the domain. Oh, sorry, the uniform continuity. Okay. So in uniform continuity, okay. So say that again. Correct. Right. Yes. Okay. Well, not 51 delta, 2 into 51, right? Yeah. The geometric sense is that if so there is a domain where x lives and the range where f lives, right? The mapping is taking x to f of x. So geometrically what is happening is if I'm squeezing the 2 points over here, I'm also squeezing by a proportionality constant over here. That's what the math is telling me, and that is what is happening. If I'm squeezing over here, the proportionality of squeezing in the range is related. Is it related to the point at which I'm squeezing? Then it's continuous. If it is not related to the point where I'm squeezing, it's uniformly continuous, right? So if I take 2 points whose distance is 51, their map will give me f, which is 51 multiplied by some constant apart. Okay, that's fine. Now, can you make it, is that going to be true for all pairs of points I can take? If yes, then you have one of these two notions of continuity. Does that satisfy the geometric intuition? Okay, good.
Is it Lipschitz continuous?
Is it Lipschitz? Can you define, I'm getting ahead of myself, but can you define the derivative at the kink? So, that may still not, but the piecewise derivatives are finite. So, you may be able to get by. Yeah. Yeah, but delta squared, I can just define new constant kappa.
Yeah, but if you just put delta behind,
but that you are generalizing from one example, no? It may not. Yeah, I'm not sure. I mean, we can look more. So, by the way, the rest of you, if you are done, you can give your feedback chit to either me or Sai Sanjay and head out.